Arrhenius equation is a mathematical expression that connects between rate constant with activation energy and temperature. So this is the original of Arrhenius equation, which is rate constant K is equal to constant value A exponent to the power of negative activation energy divided by RT. So from this equation, we can see that activation energy related to rate constant. So how activation energy related to rate constant? Lower activation energy, high rate constant. We know that from rate law, rate is directly proportional with K. So higher rate constant, higher rate of reaction. Okay, another relationship is temperature with rate constant. Higher temperature, higher rate constant. Okay, so rate constant higher, rate higher. Okay, so activation energy low, higher rate constant, higher temperature, higher rate constant. So we will use this equation when the question only give one temperature. Okay, we will use this equation when the question only give one temperature. So temperature must be in unit Kelvin. Okay, activation energy, the normal unit will be kilojoule per mole. So when we want to calculate using this equation, we need to convert kilojoule per mole to joule per mole. Okay, because R is in unit joule. Okay, we have another equation, but this one is derivation of Arrhenius equation only to plot a graph. So this is a derivation from Arrhenius equation. We derive this from this equation. Okay, so we only use this equation to plot a graph. Okay, we never use this equation to calculate something. Okay, so according to this derivation of Arrhenius equation, y-axis is ln k. When you learn something, there will be no unit. X will be 1 over T, so it must be in Kelvin. So your y-intercept is ln A. So your y-intercept will be ln A. Okay, so we only use this equation to plot a graph. Okay, so this is the example. So given the value here, rate constant and temperature in Kelvin. So determine graphically the activation energy for the reaction. So we need to plot a graph of ln K versus with 1 over T. So ln K is equal to negative EA over R 1 over T plus with ln A. So your Y will be ln K. So given K here, so you ln the value, so you will get negative. And then here you have temperature already in unit Kelvin, so no need to change anything. So you just need to calculate 1 over T. So the slope of the graph will be negative EA over R. So I only want to find EA only. So R is a constant value, 8.314. So from this calculation, we will get EA in unit joule. Standard unit for EA will be kilojoule. So from joule, you need to convert the value to kilojoule. Okay, so we have another equation in Arrhenius. This one we will use for calculation, specifically when we have two different temperatures. Okay, so this is the original equation from Arrhenius. So this one we will use when you have only one temperature. Okay, so we will use this equation when the question provide you with two different temperatures. So ln K1 over K2 equal to activation energy over R 1 over T2 minus 1 over T1. Okay, temperature as always must be in Kelvin because R is in unit Kelvin. EA must be in unit joule per mole because normally in exam it will provide you with kilojoule. Okay, so the decomposition of hydrogen iodide, so given the equation, has a rate constant, this value at 500 Kelvin, and has another rate constant at 600 Kelvin. So the question asks you to find activation energy. So when you have two different temperatures, so you need to use this formula. Okay, so R is a gas constant value. Temperature must be in Kelvin. So the question already give you in Kelvin. So this is your K1, this is T1, this is K2, this is T2. So we insert the value. R is a gas constant. Okay. So when we press the calculator, we will get EA is equal to 175,923.6 joule per mole. Okay, so from the calculation, the unit of EA will be joule per mole because R is in unit joule per mole per Kelvin. Okay, so standard unit for activation energy will be kilojoule. So this value need to divide by 1000. So your final answer should be in unit kilojoule. Okay, we look at another example. The rate constant for the first order reaction, so this is the rate constant, so this is K1, and then given that temperature T1, what is the rate constant? So we want to find another rate constant at temperature 350 Kelvin, so this one is T2. So when you have two temperatures, two rate constant, so you need to use this equation. This equation specifically for two different temperatures. Okay, if the activation energy is 50.2 kilojoule per mole. So we just write down the equation, but then for activation energy, you need to convert into joule. Okay, then you can cancel joule, joule, and here you can cancel Kelvin and Kelvin. Okay, so given in kilojoule per mole, so we need to convert that one into joule. How to convert? Times 10 to the power of 3. Okay, so in the equation, you need to use joule. Okay, so we press calculator and your answer should be 0.702 per second. So K1 and K2 is actually same unit because this is the same experiment but then in different temperatures. Okay, eksperimen masih sama, masih lagi first order. Eksperimen masih sama. Yang berubah hanyalah temperature sahaja. Okay, so buat summary sikit. So again, ini adalah original Arrhenius equation. Kita gunakan equation ni bila soalan bagi satu je temperature. Ataupun soalan minta Arrhenius equation. Kita kena tulis equation ni lah. So dalam equation ni ada relationship yang kita perlu tahu. And then ini adalah derivation from Arrhenius yang kita gunakan hanya untuk plotting graph. Okay. And then last equation, this one is also derivation for Arrhenius, tapi kita akan gunakan this one specifically untuk calculation bila soalan bagi dua temperature yang berbeza.